Hello, my name is Edgar Gephardt, and this is the first lab, the Charged Tapes Lab. The purpose of this lab was to determine approximately how much excess charge is on one piece of charged clear tape. The basic models that I used during this experiment were Coulomb's law, which states that the electric force is equal to the K constant times the charge 1 times charge 2 over the radius between the charges squared, the electric field equation, the electric force on a charged object equation, which says that the electric force is also equal to the electric field times the charge of the charged object, and then just simply gravitational force. The force of gravity is equal to mass times the gravitational constant. And to preview our results, the excess charge calculated on one piece of clear tape was 1.35 times 10 to the negative 8 coulombs. So in this case, the system is our two pieces of U-tape, and we're going to say the surroundings are the earth and the air, and we are only going to consider electric and gravitational forces. So first I put a base tape of length 0.20 meters, or around there, onto a desk, and create an equal-sized U-tape with a handle, which I stuck onto the base tape. I then ripped off the U-tape and put it aside, or the upper tape, on the table, and I did that 2 times. Then continuing, I tested the U-tapes. So the two U-tapes were repelling each other, meaning that they had the same charge, and then I rubbed a pen in my hair and then held it up to one of the U-tapes, and it was attracted to the negatively charged pen, meaning the U-tapes are positively charged. I then attached one of the U-tapes to 2 notebooks over a table, and I held the second U-tape up parallel until it began to float, and a distance of 0.029 meters, or 2.9 centimeters, were recorded in the movement of the top tape. So we assume that each U-tape has the same net charge, that each tape is represented as a point charge with all charge located in a single point at the center of the tape. We do not ignore air resistance, nor do we assume that charge is evenly spread throughout the tape. So our initial tape data, the length of the tape, is approximately 0.2 meters, and the mass of the tape is 0.0002 kilograms, or 2 times 10 to the negative 4. And the distance between tapes when the floating began was about 0.029 meters, or 2.9 centimeters. So, are my calculations. So for gravitational force acting on the tape, it's mass times gravity, which equals negative 1.96 e to the negative 3 newtons. And so the electric force has to counter that gravitational force in order for the floating to happen. So it's in the opposite direction and the same magnitude. The charge of the U-tape, we then use that electric force set equal to Coulomb's law, and then because the charges are the same, we can say that it's Q squared, which simplifies to Q equals the square root of the force times the radius squared over the constant, which gives us 1.35 e to the negative 8 coulombs. And to find the number of deficient electrons, we divide that charge by the number of total electrons, 1.6 e, or the total charge of electrons, 1.6 e negative 19, which yields 8.4375 e to the 10 electrons. So the fractions of atoms that gave up their electrons is, we find the total number of atoms on the surface area of the sticky side, which is 5e17 atoms, and we divide the ratio of deficient electrons over those atoms to get 1.6875 e to the negative 7 as our ratio. So to begin my coding, I set up all my constants, then I found the gravitational force, set the electric force equal to the magnitude of that, and then I set up a vector in order to find the charge using Coulomb's law, and then from there I found the number of electrons by dividing that charge by the constant 1.6 e to the negative 19. So this is what the computational readout looks like, and it gives us back approximately our values that I had calculated. So what if electrons had positive charge and protons had negative charge? So the tapes would still have the same sign of charge, and they would still repel, meaning they would still repel each other and float. So the experiment would work the same way, but they would just have different charges. So it's important to handle the charged tapes as little as possible because with an electron deficit, the tapes are positively charged, and interaction with our bodies, which are fairly neutral, could transfer electrons, removing the charge from the tapes. Other possible sources of error are excessive contact with the U-tapes, obviously, or the setup of the notebooks, inaccurate measuring, or not holding the tape parallel enough. So to conclude, my computational model was able to accurately predict the magnitude of the charge on one piece of tape, and with an absence of other forces, the electric force equaled the gravitational force in this scenario, allowing us to calculate the total charge. Thank you for listening, and I'll see you for the next lab.